more about tangents. So we learned what a tangent was in our first lesson. Today we're going to talk about some characteristics of a tangent. So our first theorem says if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. There are tons of vocab in here. So if you don't know what that means, we have no idea what this thing is saying. So we're going to break it down term by term to get straight what this thing is saying. Okay, a line is tangent to a circle. So I need a circle. I need a tangent. What did we learn a tangent was?
Meets the circle at one point.
It meets the circle at exactly 1 point. So it's just going to brush along the edge of the circle at exactly 1 point. A line is tangent to a circle. Then the line is perpendicular. What does perpendicular mean? Meets at 90 degrees to the radius. What's a radius? Half the diameter or
middle to the
center to the side. Drawn to the point of tangency. What's the point of tangency?
Where it meets the
The
circle.
point that I have marked as a dot, the point where the tangent meets the circle. Okay, so I'm going to draw a radius to that point. A radius goes from the center to the edge, and according to this theorem, that's perpendicular or makes a 90-degree angle. Okay, so a tangent connected with a radius makes a right angle. The corollary says tangents to a circle from a point are congruent. I'm going to extend my tangent out a little bit further here. And I'm going to draw in another tangent from that same point. So from that point outside, I'm going to draw in and make another tangent. And what this corollary says is if I take the measurement from the point of tangency to this point of intersection, that those two lengths should be equal.
what two lengths?
The lengths for each of the tangents from their point of tangency to their point of intersection. A corollary we learned before is something that follows directly from a theorem. I'm not sure I would call this a corollary because it's not like you can just look at it and go, oh yeah, I see. The reason would be what we would have to do is connect in again and connect there, and then we end up with two right triangles, and we would know all radii are equal to each other, and this side is reflexive equal to itself. We have a right angle, we would end up getting a hypotenuse leg congruence, and then that other one would have to be. I don't think I would call that a corollary. That seems like too many steps to be a corollary. It seems like more of a theorem, but it doesn't really matter, I suppose. The important thing is that you know that if I have two tangents to a circle that meet each other, that those lengths are congruent. Theorem 9.2 says if a line in the plane of a circle is perpendicular to a radius at its endpoint, I don't know why it says at its endpoint, then the line is tangent to the circle. Okay? Theorem 9.2 has exactly the same picture. It's just that we would know the other piece of information. So if we know we have a tangent, then we can know we have a perpendicular to a radius. If we know we have a perpendicular to a radius, then we know that that must be a tangent. Okay? So it works either way with either piece of given information. When we can say theorems forwards and backwards like that, we call them converses. Okay? And these are both true. If it's a tangent, it's perpendicular to a radius. If it's perpendicular to a radius, then it's a tangent. Okay? In the last lesson, we had a polygon inscribed in a circle, or the circle was circumscribed. So we had a shape, and we put a circle around the outside of it. Okay, so like a triangle, a rectangle, something like that. We put a circle around the outside. Here we're going to do the opposite. Here our polygon is going to be circumscribed, so the polygon is going to be on the outside. The circle is inscribed. The circle goes inside. Okay? When we do this, we want each side of our polygon to be tangent to our circle. This might fall off my board here a little bit, but pretend like that closes up and makes a triangle. That triangle would be circumscribed because the triangle is outside. The circle is inscribed because the circle is inside. Yes.
When a circle is inscribed in a polygon, does the circle have to touch all sides of the polygon?
Yes. And it has to be tangent to all sides of the polygon. A common tangent is a line that is tangent to two or more coplanar circles. So I'm going to have two circles, and a common tangent should be tangent to both of them. Okay. So that line is a common tangent. Specifically, that line is a common external tangent. An external tangent, it says, doesn't intersect the segment that joins the circle centers. So if I take their centers and connect them, that segment doesn't cross our tangent. So it's called an external tangent then. If we draw a tangent that does cross that line, pretend like that's a straight line, that would be an internal tangent. Okay. It goes kind of between the circles then. Questions on externals or internals? Last term here says tangent circles. Tangent circles are two circles. This is almost impossible to do. That are, my circle drawing tool doesn't really work good for this purpose. No, it's not close enough.
That first one.
There we go.
Oh, wow.
Got it.
Tangent circles are two circles that are tangent to each other. So they bump each other at exactly one point and don't cross into each other at all. Okay. Questions? Yes.
That red line on the two external
Mhm.
and internal, what is that just showing that they're
That's the segment that connects the circle centers. So that's what lets us know whether it's called an external or an internal. If it crosses that red line, it's called an internal.
okay, so
If it doesn't cross it, it's called an
that's
external.
just there for like visually.
All right, some examples. How many common external tangents can I draw for these two circles? Two. I could draw one that goes above and one that goes below. Okay? And those don't cross the line that would connect the centers, so those are externals. How many common internals should I draw? Two. Okay, they're going to make kind of an X through the middle here. We can get two externals and two internals there. Oops. How many common externals can I draw?
Two.
Two. I can draw one. Oops. Goes along one side of them. Pretend like that's a tangent. And well, along the other side of them. How many internals?
One.
Zero. I don't see it.
One, technically.
Again, one or none is what I'm hearing the most of here. We can draw one that's going to go through and share that point that the two circles share. How many externals can I draw?
Two.
Two. How many internals?
Zero.
0. I can't be tangent to both of those and cross through the center line without going into the circles. And tangents can't go into the circles. How many externals?
2.
2. How many internals?
0.
0. Hopefully it'll catch up here. There we go. This one I don't think I can use with the circle tool, so I'm just going to have to freehand a little circle there. How many externals?
1.
How many internals?
0.
So I can for sure draw 1, and then the question is whether this is really an external or an internal. And the way we can always tell is if we take that line that connects the centers of the two circles, our tangent doesn't cross that line, so this would be an external. And our last one. How many externals?
0.
0. How many internals?
0.
0. There's no way I can brush both of those circles. Okay, I would have to cross inside of them. In which one or ones of these would we say that our circles are tangent?
B.
B
B and E.
and E. In B and E, the circles are tangent to each other. To be tangent circles, that means they have to bump each other at exactly one point. In B, the two circles are outside of each other, so we would call those circles externally tangent to each other. And in E, one of them is inside the other one, so we would say that those tangents are internally tangent to each other, okay, because one is inside the other. But B and E are both tangent circles. Questions? Okay, homework. Because it's a break and I'm a nice person and this problem is always very difficult for students, we're going to get rid of question 10.
Yes.
And on 8, no part D. Just parts A, B, and C on number 8.
And did we do 9?
And you'll do 9 still, yeah. Number 16, a hint for you is you're going to need to look for some similar triangles and set up proportions or fractions for their sides. Okay? And in lots of these, remember our big idea theorem today, just sketching here now, is that a tangent and a radius are perpendicular. So if I end up with a picture like this, I have a special kind of a triangle, and it's a right triangle. So maybe I could use a Pythagorean theorem if I need to find a missing piece. Or maybe it's a special right triangle like a 30-60-90 or a 45-45-90. So remember that our tangent is perpendicular to the radius, and so then we're going to end up with, if we connect that, a special triangle that is a right triangle. Maybe 30-60-90, maybe 45-45-90, but you could at least use the Pythagorean theorem to find a missing piece there.